The situation involves a capacitor charged to a certain voltage and possessing an initial energy of 1/2 times the capacitance times the voltage squared. When an identical capacitor is connected in parallel, the voltage across each capacitor becomes half of the initial voltage. Consequently, the total energy of the system appears to decrease to 1/4 times the capacitance times the original voltage squared. The question arises with the missing energy, specifically 1/4 times the capacitance times the original voltage squared, has gone. The hypothesis suggests that this energy is converted into heat through current squared times resistance losses within the conductor connecting to the second capacitor. Despite the lower resistance of the wire, the initial current is presumed to be extremely high, decreasing over time due to the resistance-capacitance circuit's time constant. The energy stored in the system decreases upon connecting the identical capacitor in parallel, with the missing energy dissipating as heat because of the resistance in the connecting wire. When the second capacitor is connected in parallel, the charge initially and the first capacitor redistributes between the two. This redistribution of charge causes a current to flow through the connecting wire. The wire's resistance, even if minimal, causes some energy to be lost as heat. The amount of energy lost depends on both the resistance of the wire and the duration it takes for the charge to redistribute. The time constant of the resistance-capacitance circuit, which is determined by the resistance and the capacitance, dictates how quickly the charge redistributes. Given that the resistance of the wire is very low, the resistance-capacitance circuit's time constant will be short. This implies that the charge will redistribute rapidly, with most of the energy transferring to the second capacitor before it can dissipate as heat. However, even with low resistance, some energy will inevitably be lost as heat, as no wire possesses zero resistance. The energy loss will be small, but not zero. Therefore, the energy lost when connecting a second capacitor in parallel dissipates as heat due to current squared times resistance losses in the connecting wire. The behavior of the system can be analyzed using fundamental electrical engineering principles. Firstly, consider the initial state with a single capacitor charged to a voltage. The energy stored in the capacitor is given by the formula energy equals 1/2 times capacitance times voltage squared. When a second identical but initially uncharged capacitor is connected in parallel to the first capacitor, charge will redistribute between the two capacitors until they reach a common voltage. This redistribution occurs because connecting the capacitors in parallel creates a closed circuit, allowing charge to flow from the capacitor with higher potential, the initially charged capacitor, to the capacitor with lower potential, the initially uncharged capacitor, until they reach equilibrium. The total charge in the system remains constant during this process. If the initial charge on the first capacitor is Q, then after connecting the second capacitor, the total charge is still Q, but now it is distributed between the two capacitors. Since the capacitors are identical, they will each have half of the total charge, that is, Q divided by 2. The voltage across each capacitor can be calculated using the relationship Q equals capacitance times voltage. Therefore, the voltage across each capacitor is now Q divided by 2C, where C is the capacitance of each capacitor. Since the initial voltage was Q divided by C, the final voltage across each capacitor is half of the initial voltage. Now, let's calculate the total energy stored in the system after the capacitors have reached equilibrium. The energy stored in each capacitor is 1/2 times capacitance times voltage squared. Since there are two capacitors, the total energy is 2 times 1/2 times capacitance times voltage squared, which simplifies to capacitance times voltage squared. Substituting the final voltage, which is Q divided by 2C, into the energy equation, we get total energy equals capacitance times Q divided by 2C squared, which simplifies to Q squared divided by 4C. Comparing this to the initial energy, which was 1/2 times capacitance times the initial voltage squared, or 1/2 times Q squared divided by C, we see that the final energy is indeed half of the initial energy. The missing energy, which is 1/4 times Q squared divided by C, is lost due to the resistance in the connecting wires. When the charge redistributes, it flows through the wires connecting the capacitors. These wires have a non-zero resistance, no matter how small. As the charge flows through the resistance, it dissipates energy in the form of heat according to Joule's law, which states that the power dissipated is equal to current squared times resistance. The current flowing through the wires is not constant, it starts high and decreases as the capacitors reach equilibrium. The rate at which the current decreases is determined by the resistance-capacitance time constant of the circuit. The resistance-capacitance time constant is equal to the resistance times the equivalent capacitance. In this case, the equivalent capacitance is the sum of the two capacitances, since they are connected in parallel, that is, 2C. Therefore, the resistance-capacitance time constant is equal to resistance times 2C. A shorter time constant means that the charge redistributes quickly, and a longer time constant means that the charge redistributes slowly. Even if the resistance is very small, there will still be some energy lost as heat. This is because the current initially is very high. The total energy dissipated as heat can be calculated by integrating the power dissipated over time. The power dissipated is equal to current squared times resistance, and the current is a function of time. The integral of current squared times resistance over time will give the total energy dissipated as heat. This energy is equal to the difference between the initial energy and the final energy, which is 1/4 times Q squared divided by C. In summary, when an initially charged capacitor is connected in parallel to an identical uncharged capacitor, the charge redistributes between the two capacitors until they reach a common voltage. The final voltage is half of the initial voltage. The total energy stored in the system decreases by half. The missing energy is lost due to the resistance in the connecting wires, which dissipates energy as heat. The amount of energy lost depends on the resistance of the wires and the time it takes for the charge to redistribute, which is determined by the resistance-capacitance time constant of the circuit. To further explain the energy loss, let's delve into the transient behavior of the circuit when the two capacitors are connected. Immediately after the connection, there is a voltage difference between the two capacitors. This voltage difference drives a current through the connecting wires. The magnitude of this current is limited by the resistance of the wires. Since the resistance is assumed to be small, the initial current can be quite high. As the current flows, it transfers charge from the initially charged capacitor to the initially uncharged capacitor. This process continues until the voltage across both capacitors is equalized. The equalized voltage is half of the initial voltage, as explained previously. The current flowing through the wires is not constant. It starts at a maximum value and decreases exponentially with time. The rate of decrease is determined by the resistance-capacitance time constant. The resistance-capacitance time constant is a measure of how quickly the circuit responds to changes in voltage or current. A small resistance-capacitance time constant means that the circuit responds quickly, and a large resistance-capacitance time constant means that the circuit responds slowly. The energy dissipated as heat in the wires is equal to the integral of the instantaneous power dissipated over time. The instantaneous power dissipated is equal to current squared times resistance. Since the current is decreasing exponentially with time, the power dissipated is also decreasing exponentially with time. The total energy dissipated is the integral of this exponentially decreasing power over time. The result of this integration is equal to 1/4 times the capacitance times the initial voltage squared, which is the energy that is missing from the final energy calculation. The resistance in the connecting wires plays a crucial role in the energy loss. If the resistance were zero, there would be no energy loss. However, in reality, all wires have some resistance, no matter how small. This resistance is what causes the energy to be dissipated as heat. The amount of energy lost depends on the value of the resistance. A larger resistance will result in more energy loss, and a smaller resistance will result in less energy loss. However, even with a very small resistance, there will still be some energy loss. The initial assumption of an ideal capacitor is important to consider. Real-world capacitors have internal resistance, known as equivalent series resistance or ESR. This internal resistance also contributes to energy dissipation during the charge redistribution. The equivalent series resistance acts as an additional resistance in the circuit, further increasing the current squared times resistance losses. Therefore, the actual energy loss in a real circuit will be slightly higher than the calculated value based on the resistance of the connecting wires alone. The analysis assumes that the connecting wires are purely resistive. In reality, wires also have inductance. Inductance opposes changes in current. When the capacitors are connected, the current changes rapidly. This rapid change in current induces a voltage across the inductance of the wires. This voltage opposes the flow of current, which can slow down the charge redistribution process. The inductance of the wires also stores energy in the form of a magnetic field. This energy is eventually dissipated as heat, further contributing to the energy loss. However, for short wires and low frequencies, the inductive effects are usually small and can be neglected. The initial scenario assumes that the second capacitor is initially uncharged. If the second capacitor is initially charged to a different voltage, the analysis becomes more complex. In this case, the final voltage across the capacitors will be a weighted average of the initial voltages, with the weights being proportional to the capacitances. The energy loss will still occur due to the resistance in the connecting wires, but the amount of energy loss will depend on the initial voltages and the capacitances. The analysis assumes that the capacitors are connected instantaneously. In reality, there will be a small delay between the time the connection is made and the time the current starts to flow. This delay is due to the inductance of the wires and the switching characteristics of the connecting device. However, this delay is usually very small and can be neglected. It is crucial to recognize that the energy lost is not destroyed. It is converted into heat, which is then dissipated into the surrounding environment. The principle of conservation of energy still holds true. The total energy in the system remains constant, but it is transformed from electrical energy stored in the capacitors to thermal energy dissipated as heat.